Okay, good morning, good afternoon, and good evening to everyone, wherever you're watching us from. Um, Welcome back to our lesson in mathematics, specifically for the first year students. So, in this lesson, I'm going to talk about the concept of sets of numbers. This lesson, I'm going to talk about the concept of sets of numbers. How do I write capital letters and small letters? Okay. So the aspect of sets of numbers, in this case, obvious, what are we simply talking about? We're talking about the concept of sets. Obviously, we said that a set is basically a collection. So there will be various numbers which will be grouping into their categories. So we mentioned that a set is a collection. We mentioned that a set is collection of well-defined objects, and these objects obviously are calling them to be elements. So something which is a collection, something, the concept which is grouping there. So if I'm bringing, or maybe trying to narrow the concept of numbers, maybe sets of numbers, it means we're trying to give, or maybe we're trying to make a collection of specific numbers being categorized in their sets according to properties. So in short, what we're trying to say under this topic is that in mathematics, so we're simply saying that in mathematics, we group numbers, based on their properties. So in mathematics, we group numbers based on their properties. So the concept of grouping numbers based on their properties, this helps us understand how numbers are related, or maybe, and where a particular number belongs to. So there are a lot of numbers in the world, but trying to understand these numbers in the world, that is why we're trying to group them according to their properties. So this is a lesson we're having today, where we're trying to understand some concepts of sets of numbers, though I'll try to narrow it and basically focus on one type of numbers, but I'll try to explain all of them in this lesson. So there will be the concept of number one. We are going to have an understanding of the first concept, which is called a natural number set. So we have the concept of natural numbers there. So now the question comes in to say, what is a natural number? So this is a set, meaning it's a collection. So I'm collecting numbers. So even as I'm collecting numbers, there are specific numbers I'm basically just collecting, not any just types of numbers, because there are a lot of numbers in the world. So for me to collect a natural number set is a collection of basically counting numbers. So these are counting numbers. Starting from starting from 1. So basically what we're trying to understand is that the natural number set n is basically equals to 1, 2, 3, 4, 5, and the count continues. Every counting number starting from 1 is going to be called a natural number in this case. So if I look at the aspect of natural numbers, you are just talking about the normal natural number, the normal numbers we know from grade 1, where when we start counting, when we are learning to count, obviously we started to learn to count starting from 1. Let's start starting from 1, we count 1, 2, 3, and we continue counting until I don't know. So the count is basically endless. That is why it is called a natural number. So counting numbers, a collection of values which are called to be counting numbers. So these which I have here, I don't have decimal numbers in here, I don't have fractions in here, I'm just having basically what? Specific whole values starting from 1 until I don't know. So there is another concept here which we're trying to embrace again, the concept of whole numbers. The concept of whole numbers. So under the concept of whole numbers, we're trying to define them as they are basically just counting numbers starting from 0. Or others would simply say these are natural numbers, including 0. So if I was to include 0 in the natural number set, what type of set am I going to have? I'm going to have a set of whole numbers. A set is a collection. This is a set of natural numbers. This what I'm going to make up. Natural numbers plus 0 will have a set of whole numbers. So I'm now going to have the set of whole numbers represented by W. So this W will be equals to 0, 1, 2, 3, 4, 5, and the count continues just like that. So we have the concept of natural numbers and we have the concept of whole numbers from there. The other aspect or the other idea which you have to understand is the idea of integers, which is number 3, integers. So if I look at natural numbers here is basically whole values. I don't have any fractions, I don't have any decimal numbers, it's just basically whole values. Whole numbers as well, they're just basically whole values, whole items. So in integers here, we're just trying to look at the aspect of positives and negative whole values, whole numbers, including 0. So if I combine, remember the natural number is going to make up a whole number because it is in the whole number that I have natural numbers. The only thing which is not included in the natural number is 0. So 0 plus natural numbers makes up whole numbers. So these whole numbers plus other negative whole numbers, they will make up integers. So integer set is made up of positive and negative whole numbers. That is why the Z, the symbol for integers, is basically equals to all the negative numbers we can think of. Remember, it's negative whole numbers, not fractions, not decimals. We're just talking about whole numbers. So negative whole numbers, maybe we have a lot of negative numbers coming from this side. So I can list it starting from dot, indicating that there's 2 more numbers this side, maybe negative 3, negative 2, negative 1, 0 included, 1, 2, 3, and the count continues with 3 dots indicating that it is still endless. This side is endless, even that side is endless. They are whole numbers, positive whole numbers and negative whole numbers. At the same time, we are including a 0. Well, okay. And then what I have here, natural numbers, whole numbers, and integers are basically trying to understand the aspect of whole values. They're just basically whole values. I won't find any point or any decimal number in it. So, but when I now trying to move in and understand the aspect of the other collection, which are going to be rational numbers now. So under rational numbers, we are looking at the fraction number coming about here. The same decimal numbers as well coming about. So that is why we're trying to define this number as a number or a value that can be expressed in the form a over b. So this guy, a rational number, should be expressed in the form of a over b, where a and b should be from the integer set. So what am I seeing? Natural number plus 0, it will make up whole numbers. Whole numbers plus other negative numbers, it will make up integers. So from the integer set here, we are simply grabbing any two values, a and b, to make up something which is called a rational number. So for example, I was to grab a to be 1 and b to be 2, I'm going to have something like a 1 over 2, which will be a rational number. If I was to grab 1 and 3, I can have 1 over 3 as a rational number. So all these values are going to make up rational numbers. So from the rational number set, I can basically form a rational number set from the integer set. So it's rational, that's why I'm going to find decimal numbers. 1.5, 0.5, and so forth. But when I'm listing integers, I'm just listing whole numbers. But when I'm listing rational numbers, even decimal numbers they are also being listed. That's what we're trying to talk about. And then there is another opposite of this, which we are calling to be irrational. Irrational numbers are basically those numbers. Maybe I can just delete up. So if I look at the other concept, which is called irrational numbers. So irrational numbers is basically the opposite. Irrational numbers basically is the opposite of rational. These ones here, they can not be expressed. They cannot be expressed in the form a over b. Example which we can talk about here is the square root of 2. So if I look at the square root of 2, they are different. There's a difference between a rational and an irrational number where I talk about 0.5. 0.5 has a definite end, meaning that the end 1 over 2 can be expressed in a decimal number 0.5. It has a definite end, or maybe a terminating decimal for the decimal numbers I have. They are terminating. But if I look at root of 2, if you punch on your calculator, you'll find that this number has no terminating decimals. So it will be something like 1.41421 So what I'm seeing is the numbers are not repeating. At the same time, they don't have an end. They will just be continue moving just like that. All these numbers which have such cases, it is difficult to express them in the form of a over b because they don't have a definite end in terms of their decimals. But something like a 1 over 2 can have a definite end. So that is irrational. So the major numbers that time which I've talked about, we're talking about the natural number making up whole numbers makes up integers makes up rational numbers. And those which are not in this format are basically irrational. That's where number will have the general aspect of something which is real. These numbers which are according to be real numbers which can be quantified in something which is real in real life situations, which are now going to be real numbers. So this time around, we're now trying to look at the aspect of real numbers. What are real numbers? So real numbers here are just basically a combination of rational plus irrational. So these are all whole natural numbers. So we're talking about natural numbers, we're talking about whole numbers, we're talking about integers, we're talking about rational. Rational is basically capital letter Q. That's a denotation for rational numbers. Irrational numbers, we're talking about the capital letter Q we can have, none can, implying that complement. So a collection of all natural numbers, whole numbers, integers, rational and irrational numbers will make up the real number values. Okay, then? So these are basically the collections of numbers which we have to know in mathematics. So if these are the numbers which we know in mathematics, now my focus for today is just trying to highlight the concept of real numbers. The concept of real numbers. Now look at this. We are able to list natural numbers. We are able to list whole numbers. We are able to list integers. Though, yes, we can be able to list rational numbers. Sometimes it will be difficult to list all the rational numbers because there will be a lot. So, certain values which you can just limit and list as well as irrational. The same comes to real numbers. For me to list all the real numbers, it's basically difficult. So we denote real numbers in interval form. So our focus which in this class, which I'm going to now talk about, is understanding the concept of real numbers. I'm going to delete everything now, then narrow it to real numbers. So now I'm now talking about real numbers. After understanding all these aspects from natural numbers to real numbers, we know that real numbers is made up of all the numbers in the world. That is from natural numbers, whole numbers, integers, rational and irrational. Together combined, they make up the real values or the real numbers. So we are simply saying that it is difficult to list all the values in the real number set. So in the real number set, it is difficult to list all the real values. So what do we do? Hence, we use intervals to list or to represent a collection of real values. So we are going to be using intervals. E.g., I can say that the real number set R is basically equals to x such that x is x such that x, or maybe I can say negative infinity is less than x and x is less than positive infinity. This can be a description of the real number set. So negative infinity is representing the smallest value we can think of in the world. Positive infinity represents the highest positive value we can think of. So mathematically, when we start counting, remember something real can imply the whole numbers in here, rational numbers in here, integers in here, irrational in here. Everything is embraced in that interval. So that is why I'm simply saying we use intervals to list or represent a collection of real numbers. So if I'm trying to represent a collection of real numbers, this will be my real number set. So all real numbers will basically run from negative infinity to positive infinity. So it means if I was to collect maybe certain values, maybe from 5 to 6, 5 to 6, there are a lot of real numbers in between. So that is why we can list them all. Just 5 to 6. If I just say list values from 5 to 6, all real numbers from 5 to 6, there are a lot of values here from 5 to 6. Maybe 5.1 is also a real number. Someone is going to say 5.2 is also a real number. Though here I've just limited, I've also skipped a lot of real numbers in between here, which can be maybe 5.01 is also a real number, which can be 5.001. This is also a real number. So those even smallest digits, smallest decimals, are also be found in real numbers, because we're not only focusing on whole numbers. So there are a lot of real numbers between just 5 and 6. There are a lot of them. So that is why when listing these real numbers, it is difficult to list. Hence, the aspect of intervals comes in. So we have to use intervals. So that is why I'm saying that a real number can be written as x such that negative infinity is less than x and less than positive infinity. Negative infinity represents the smallest digit. So if this is my number line, there is a negative infinity this side and there is a positive infinity this side. This is my real number line. Obviously, there is a zero in between. So from here to there, this is my real number set. So hence, in interval form, the r, which is a real number set, can also be written as x is a member of negative infinity, positive infinity, in that manner. Though we'll have to look at the meaning of how to represent such cases. So this description can be the same as that description. So now, let's look at the aspect of what is an interval. What is an interval? So, from the aspect of what intervals are, what are we simply saying? We are simply saying that an interval, in simple language, we are simply saying an interval is a subset of the real number line. A subset of a real number line is basically an interval. Or somebody will just simply say in simple language, a portion or a part of the real number line. That's the interval. So it means that if this is my real number line running from negative infinity to positive infinity, then I have a lot of values in between here. Whole numbers, natural numbers, irrational numbers, integers, a lot of values. So if I was to have maybe -7 falling there, maybe I have -3 somewhere there, a 0 there, a 2 there, a 6 there. I can break this down into intervals. Maybe from -7 going into this direction, this is a portion on itself. This part is an interval. It is not the whole real number line. So the real number line is from negative infinity to positive infinity. So a portion or certain part, an interval is basically a range of values from what to what. So this is a range of values being collected. This can be an interval. Maybe from here to 0, this also can be an interval. Maybe from here to 6, this also can be an interval. So it's a portion or a part formed from the real number line. So if it is a portion or part formed from the real number line, every portion is called an interval. So there are a lot of values in between here, not only whole numbers, but even decimal numbers. That is why it is difficult to list all the values which are here. So if I start from -7, there's -7.0000001, -7.0000002, -7.00003, -7.00004, until maybe I reach -7.9. Again, yambo konkamo put 1 point shan and so forth. Until maybe I reach -8. From -8 again, I count all the numbers. There are a lot of real numbers in between here. So these are portions which are going to be intervals. So if that is my interval, we're simply saying representing a real number line set, we use intervals. So anything coming from the real number line, anything which coming from the real number set, we'll use intervals to describe such a set. So the best is to use the intervals. So we'll look at representation of these intervals. We'll now look at the aspect of representing these intervals. How basically am I going to represent these intervals? This is what we're going to look at in this period or this time. So representation of intervals. So let me just delete this part. We can look at now by the aspect of representing intervals. So with that understanding number, we are now looking at the aspect of how these intervals can be represented. Intervals, we are looking at an interval being a subset of the real number line. A subset of the real number line. So there will be cases whereby we'll be looking at, because these intervals can be represented in inequality form or interval form and so forth. So what are we going to be looking at? I'm going to describe a table to describe certain intervals which we'll be looking at. So let's say we're going to have an inequality. I'm going to have the aspect of the notation on how we can represent that inequality in interval form, the notation interval. So let me say interval notation here. And we'll create some space. Interval notation, we are going to have a column for the interval type. We are going to have a column for the number line. Remember, an interval is basically a portion from the real number line. So if this is my table, we're going to talk about values which can be in this format. So we're going to have values which can be in this format. So for example, if I tell you, say, can you give me a collection of values where x is greater than or equal to a? X should be greater than or equal to a. You know what values you are collecting. Anything more than or equal to a is basically your collection, isn't it? So if I look at my number line here, obviously if a is here, my number line is running from negative infinity to positive infinity. So if I stand at a here, I'm looking at where the collection is greater than a. That's where you're trying to collect. So greater than a here, I'm opening my bubble at a. I'm going to the greater than side, which is my right direction. It is this direction. So what am I saying? X greater than a, it is this portion. So this interval here represents x greater than a. But it is not just greater than a, it is also equal to a. So at this portion where I'm opening my bumble in the number line, I'm also supposed to shade it, indicating that this portion is not just greater than, but it is also greater than or equal to a. This is what we mean. I'm going to my right direction. In a situation whereby I had x is greater than a alone, what happens? I'm going to have my number line in that manner. If this is my a, I'm opening my bubble at a, I'm still going in that direction, but my bubble here will be what? Will be open. It means that what I'm collecting is just basically values which are more than a but not equal to a. So a is just basically acting as my boundary. So for example, if this a was 2, it means I'm collecting values which are greater than 2. It means 2.001 is part of this interval, but 2 is not part of the interval. 2 is just acting as the boundary to say don't cross over to the other side, but the values you are looking for are coming from this direction. 2.1 is part of my solution, but 2 is not part of my solution. So in interval form or interval notation, how do I describe this? Because this is a portion in interval notation. This is why we're trying to write, say, x is a member of a, comma, positive infinity, implying that the lowest bound is a, the highest bound is going to be the greatest value. So since it is also greater than or equal to a, we use the notation of a square bracket to represent that it is also equal to. But for this one, it is x being a member of a, comma, positive infinity. Actually, a oku, it is not equal to a, it will be a round bracket, emphasizing it is open oku a. So this means it's a closed, but this one is an open one. So infinities are never closed. That's the information which you have to understand. Infinities are never closed. These are just basically representation of certain values which are going to be the highest value or the smallest value. So this is the highest value. If I tell you to say start counting and reach the highest value, you'll be counting and you will count no more because you will never reach the highest value. So this side, Euclid infinity, it is always round, not square. So this type of interval which is closed on one side and open on the other side is basically called a half open interval, or others will say semi-open. This is basically open on both sides. It's basically fully open interval. So it means it's an open interval. You okay? So the same is happening. I'm using a greater than symbol here to describe what I'm collecting. Remember, talking about the real number line. So the real number line means for me to describe, I'm going to use inequalities or intervals to collect that set. So I'm saying just go collect x greater than 2. It means I'm going to collect all the values which are greater than 2. They are all coming from the real number set. Or maybe we say go collect x less than a. This time around, I'm talking about values which are smaller than a. So values smaller than a, if this is my a here, smaller than side is going to be to the other direction. So if it was x is less than or equal to a, it means that even the a here bubble will be shaded. I'm going in that direction. So this side is x less than or equal to a. This one was x greater than a alone. But if I had x is less than a without equality, this manje becomes from a, you open your bubble, you go to that direction. This bubble will be open and not shaded. This is the kind of description we're going to have. This is what I'm going to have. So what is the interval notation for this? This is less than. So less than, I'm going with the smallest value. Every time we're trying to write something in interval notation, the first value should be smaller and then the last value should be the highest. So it's the least bound, comma, the upper bound. So the least bound when it is less than a, the least bound I can tend to attain, I'm going to negative infinity, comma, the upper bound which will be the a itself. This is closed and this is open. This one will be x, comma, negative infinity, comma, a. This is open and this is open. So that we can now have this as what type of interval? It is closed on one side and open on the other side. It means it's also called a what? A half open. This one is all completely what? Open interval. So these are some of the collections which you have to take note of. But there will be some other collections where, in this case, I'm going to collect my value of x, which is in between two bounds. So the type of inequality I can basically use are maybe a is less than x, at the same time x is less than what? B. What does this mean? So this means my x is in between a and b. So if I was to try to look at a number line here, obviously there will be a somewhere and there will be B somewhere. So it means I'll open my bubble at A and B, connect. This portion, this interval, represents A less than X and X less than B. They are all open bubbles because they don't have equality. So this means it is X member of, we always start by the lowest. The lowest is A, comma the highest B. This is how it's going to look like. So what type of interval is this? This is basically an open interval. I'll have a situation whereby I have A is less than or equal to X and X is less than B. A is equal to, but B is not equal to. So this means it's X member of A comma B, but could A it is equal to, it means it is a square bracket. Could B is not equal to, it will be a round bracket. So this is a half open. How do I describe this on a number line? A, B. So A, it is open, I mean it is shaded bubble, but B it is an open bubble. So this will be the description. So I have a situation whereby it is A less than or equal to X and less than or equal to B. Equal to. So this means X is a member of A comma B, closed, closed, and this is a what? A closed interval. So it means both bounds will be closed at A and at B. You open and you shade. So this means this. So when it comes to the real number line, this is what we're trying to be looking at. We're trying to give a certain description. So it can either be described in inequalities form or it can be described in interval form. So a real number line set can be described in the form of an inequality or in the form of an interval form. That's what we're trying to say. So every time when you're looking at sets which have been described as a real number line, the best way to answer that question is through a sketch or maybe through intervals or inequalities. So let's look at a certain question. Let's look at a certain question which we can look at as an example. I'm sure you're copying, jotting down. I can delete my board. You can pause and so forth. So I'm going to work with this example from your tutorial sheet. So the example here says that this says let A be equal to X such that X is a member of all real numbers such that -4 is less than or equal to X and X is less than 2. That is my A. And we are being told that B should be X, member of all real numbers, such that X is greater than or equal to -1. So these have been described for us. So these have been described for us. These have been described for us. So find number 1, A intersection B. Find number 2, A complements. This is what we are trying to look at. A intersection B and find A complement. So what are we going to do? This is the real number set. So every time there is the concept of real number set, we can't list the real number values. There are a lot. So the best way of denoting a real number line maybe is by sketching. So we'll have to sketch we will need to sketch. So first thing, we'll sketch our set A and we'll also sketch our set B. So solution. So from my real number line, what do I have? I have from -4 to 2 as my A. So if let's say this was my 0, maybe I can have -1, -2, -3, -4, -5, -6, and the count continues. This side I have 1, 2, 3, 4, 5, 6, 7, and the count continues. I'm using these numbers not necessarily just to say that I'm not talking about whole numbers. No, it's just basically a direction. This is also embracing my decimals as well included. We're not just talking about just listing whole numbers, no. Even decimals are also included. So the best is you sketch on your number line. So when sketched on the number line, what is my A? A is -4 less than or equal to x and x less than or equal to 2. So remember the graphing of this interval. This is A less than or equal to x and x less than B. So how did we sketch? We go to -4. Open my bubble at -4. Is the bubble going to be closed? Because of equality, it's supposed to be shaded. You continue up to what? +2. +2 does not have equality to be an open bubble. So this part here is our nyumba ya set A. This is my set A. I now look at set B. What is set B? Set B is made up from -1 greater than. So -1 is here. I open my bubble there. It is also equal to, I shade. Which direction is going to? Greater than, to the right, going in this direction. This is my B. So this is my B. Then start answering. When I say A intersection B, A intersection B means what? Elements found in A at the same time found in B, isn't it? So look at where we have common items, where the two shadings are meeting. So automatically you can see that where B and A are meeting from, it is at this particular point and that particular point. So found in both. So I'm seeing that my set A intersection B is basically X being a member of the interval from -1 way up to 2. Ask yourself the type of brackets you're going to use. -1 is shaded in B and shaded in A. It is also part. So it means this would be also in the intersection. But for +2, open in A but closed in B. So 2 is not an intersection, it is just round. So maybe giving my answer as exact as they had given it to me, therefore A intersection B becomes X member of the real number set such that -1 is less than or equal to X and X is less than 2. This is my intersection. So that from there I can now find the complement. So how do I find the complement now? A complement. A complement is simply locating for elements not belonging to the A. So if this portion is my A, I'm looking for something outside A. Something outside A, it is from here going in that direction and from here going in that direction. So from what I can see here is A complement is made up of X is a member of -4 going to the -infinity. So it means an interval always starts from the less than, the smallest. The smallest is -infinity. So it means -infinity, -4. And I also have from 2 going to the right. So I also have 2 going to the right to +infinity. Then I look at the brackets number. Here -4 was shaded. It means it is in A. I'm looking for something which is not in A. So if negative 4 is in A, this will not be closed but will be round. 2 here is open, it means it's not in A. So if 2 is not in A, we can include it in the A complement by with a square bracket. So infinities are never closed, they are always round. So it is either this or that. Connecting these two intervals, we are using a union in between. So this is the A complement. So if you want to write it in this form of description, therefore A complement becomes x member of real numbers such that negative infinity is less than x less than negative 4 union 2 less than x less than infinity. This is equal to also that. This becomes a description of A complement. As simple as that. So this is one example which we have there. Let me look at the last example which I'm going to give. You can delete. So this last example is as follows. We are being told to say, let A be equal to negative 9, 9, and this be the universal set. So let A from negative 9 to 9 be the universal set, and x be equal to round negative 1, 5 closed. Y is going to be equals to negative 5, 3 closed, and z is equals to negative 1, 7 round there. So for each of the following sets and display it on the number line, find each of the following sets. So we're finding each of the following sets. Number 1, I want us to find x complement. Number 2, I want us to find A minus x. Number 3, I want us to find x intersection z complement. And lastly, I want us to find y minus x intersecting with z. As usual, we're talking about intervals. These are intervals. It means if they're intervals, the best is sketching for me to find anything. So we start. Solution. So here the key point is you locate what is your universal set. In the previous, the universal set was basically the real number line R running from negative infinity to positive infinity. Here we have another direction. This universal set is negative 9 to 9. This is your guide. It means there should not be any value, anything which I should find which is going to be more than maybe away from this interval. All the values should be limited to this interval. That's the guide. So my real number line is going to be from negative 9 to positive 9. That's my universal. And like from negative infinity to positive infinity, because the universal here is basically A. Paja, in the previous lesson, it was the real number line R, that is negative infinity to positive infinity. But with this one, the universal is negative 9 to 9. So this is where my values are going to be. So if this is 0, obviously this is -1, -2, -3, -4, -5, -6, -7, -8, until -9. This is a 1, this is a 2, this is a 3, this is a 4, this is a 5, this is a 6, this is a 7, this is a 8, and this is a 9. So running from -9 to +9, all this is basically my universal set A. So sometimes just the way I have done here, this already this line by line is my A. I can now just start putting X, Y, and Z. So X and Y is running from -1 to what? To 5. Isn't it? So now keep in mind that the universal set is not closed, it is basically open. So hapa ni -9, hapa it is open, na hapa +9 it is open. So this is my universal. It is not shaded but open. I look at X is running from -1 to 5. -1 is here, you open your bubble to +5, you open your bubble. So upper the 5 it will be shaded. You join the 2. This is the X. So if I'm looking for X complement, I'm talking about outside X, not inside X. So therefore, X complement becomes what? X complement becomes this becomes what? Something which is outside this side and outside. So I'm talking about from -9 to -1, and I'm talking about from 5 to 9. So -9 here it is still round, but -1 here it was open in X. So I'm collecting something outside X. It means -1 is outside X. So it will be closed when I'm trying to collect for the outside of X. 5 it is closed in X. It means it is inside X. If I'm collecting something outside X, it will be round there. For 9, as usual, it's a universal. So since I have two intervals here, it is either this or this. We join them by a union symbol there. So this is my X complement. So this is my X complement. So if you look at this and you look at A minus X, it's basically the same. So M minus X means in the universal set A, this is my universal set A, remove the part which is X. So I'm going to remove this portion. If I remove it, what portion is going to remain? It is this portion or that portion. So basically A minus X is the same as what? X complement. Because in this A, we are removing X. So I remain within -9 to there and from there to there, which is the same as -9, -1 union 5, 9. This is still the same solution. And you are done. 3. X intersection Z. What is coming about here is a third concept number of bringing in the Z. So we have Z already, we have X already. Let's try to describe Z. So Z is starting from -1. This is still -1 here. So I can open my bubble at -1, going to +7, somewhere up to there. Connect the two. But -1 is shaded here. Remember at X it is just open. Here at 7 it is open. So this part is basically my Z. So if this is X and this is Z, where am I having the intersection? The intersection between Z and X, it's basically this Cartesian arc. From -1 to 5, that's where Z intersection X is. So I'm looking for X intersection Z but complement. This is what I'm looking for. So for me to find this, I have first of all to find X intersection Z. and x intersection z is from -1 to 5. So it is -1, 5 is x intersection z. So x intersection z is -1, 5. So -1 is not an intersection, it is round. Why is it round? It is open here but closed there, so it means it's not belonging to both. 5 is belonging to both, but it's shaded and shaded there. This is closed. So if this is my x intersection z, therefore what would be my x intersection z complement? It means it's outside this. So outside -1 and outside 5. But there is a limit ending up to -9. So therefore x intersection z complement becomes from -9 to -1, -9 to -1, and from 5 to 9. 5 to 9. So this is what I'm going to have. So -1 to -9. -1 is not in the intersection, so it means it will be in the complement. -9 as usual, it is still round. +9 it is still round. 5 it is closed, but it will be round there. So this will be the complement of x intersection z. So this is what we are going to have. So when I now go to the fourth question, y minus x intersecting with z, what do? Y minus x intersecting with z. I'm now trying to put in the y coordinate number from -5 to 3. So the y is now going to move from -5 way up to 3. This will be my y. But both of them are shaded. So you start by first of all collecting y minus x. This is in y, but remove this x part. So x is running from here to there. So x is running from here to there. So if I remove this portion in the y, I'm going to remain from here to there. This is what I'm going to remain with. So I'm going to remain from -5 to -1. And then from -5 to -1, is there any intersection with z? There is no intersection with z because z starts from here to there. And if I remove this part, I'm going to have y minus x just alone is just basically from -5, -1. This is what is going to happen. But z is from -1 to that side. So there will be no intersection between these two. So it means somehow, if you look at this solution here, should be an empty set for that guy. So just finish it up that as your task and send in my solution. So for y minus x intersecting with z, I've already tried to open up your mind. Y, there's z and there's x. So y minus x means remove the x part from the y, you remain with this portion. So for this portion, is it intersecting with the z? Obviously it is not, and the answer should be empty set. So this is how basically we'll be solving real number questions from the aspect or the knowledge of what? Of the real number line. So with that done, I'll end here for today. So yeah, I'll end here for today. Otherwise, thank you very much for your time, and you can submit the tutorial sheet MA110 tutorial sheet 1 for question 6, C and D in tutorial sheet 1 MA110. So question 6, C and D MA110 tutorial sheet 1. You can submit to our inbox and we'll basically comment. Thank you very much and have a blessed evening, night/day.